Today, we're extremely pleased to be hosting Elise van der Poel. She previously completed her PhD in Amsterdam with Max Welling on topics of symmetry and equivariance in RL. And now she's moved on to Microsoft Research, where she's working on applying the same kinds of ideas, but for actual scientific problems. So without any further ado, thank you very much, Elise.
Thank you, Alex. Yeah, so as the title slide, I put kind of a mouthful. It's like symmetry and structure in single and multi-agent RL, and also AI4 Science. But I think it's okay because it kind of doubles as a table of contents, because it's also what I'm going to talk about, and it's also the order in which I'm going to talk about. So my name is Elise van der Poel, and I'm, like Alex said, at Microsoft. So at Microsoft Research, AI4 Science in Amsterdam, I'm a senior researcher working on reinforcement learning and deep learning for molecular simulation. And before this, I worked on symmetry and structure in reinforcement learning in Amsterdam. So if during the talk you have any questions, please feel super free to just interrupt me. It's always nicer to have a bit of a conversation than just me monologuing to you. But if you don't interrupt me, that's exactly what I'm going to do. If after the talk you have any questions or you want to know more, you can definitely just email me. You can reach out to me on Twitter, but I'm actually trying to move on a little bit to Mastodon. So if you have that, then you can also reach me there. All the papers that I'm talking about today, you can find on my website as well. And for most of them, there's also code available. I'm assuming I don't have to explain to you why like reinforcement learning and planning and decision-making algorithms are awesome, but I will give you the motivation slide just in case. So we're very interested in learning from interactions with the environment. This is kind of the pinnacle to me of AI, that you have some agent and it's walking around the world and it's interacting and it's getting better over time just from getting some feedback signal. So this application is everywhere. Autonomous driving is one that was very hyped for a while. I don't know what's going on there right now, but it used to be kind of a big thing. Robotics is a big one. I talked to a lot of roboticists today, so that's definitely a very cool application. Though I'm not sure how much RL they're actually doing on robot learning, but we'll see later that there's definitely some people working on this topic. Traffic light control is an application that I'm personally quite fond of, where you have a traffic light and you need to learn how to maximize throughput on a road network and minimize congestion. And there's also a lot of work, especially in the industry, on using reinforcement learning to improve recommender systems. Some other applications that I personally think are quite cool are on designing new things with reinforcement learning. So put a few on this slide here. So you have molecular design, you have chip design, you have network planning, but I also heard a little bit today about evolving robot morphology. I guess you could also do that with reinforcement learning, but I don't know if people have tried. And I'm also going to skip the long-winded introduction about what reinforcement learning is and just assume that I only need to remind you. Is that right? Or should I actually go through the long-winded introduction? All good? Awesome. Okay, in reinforcement learning, just as a recap, we care about learning from trial and error. So some agent that interacts with the world and gets some feedback signal and then tries to improve its behavioral policy over time. Don't worry about it. So this is the notation that I will be using today. I'm mostly going to be basing everything on the Markov decision process, or MDP, where we have a space of states, a space of actions, a transition function that gives you the next state for a given state action pair, stochastically or deterministically, and a reward function that for a given state action pair gives you a reward, deterministically or stochastically. And the goal of reinforcement learning is to find some policy that maximizes the cumulative reward over time. Now, most of my research is motivated by the fact that reinforcement learning tends to be quite data hungry. This is a bit of an older plot that I made a few years ago, but I think it still holds for a large part. Here I plot the number of data points in specific computer vision data sets, the ones that we all know and love. So you have your MNIST, your CFAR, and your ImageNet. And I plot them against the number of samples used by some, at the time, quite popular model-free reinforcement learning algorithms, mostly I think for Atari games. And you can see that even something like ImageNet is completely dwarfed by the number of samples that reinforcement learning algorithms use for even something like a simple video game. And that will be fine if we just have a huge data center and we can just run everything in parallel. But in practice, very often this sampling is quite slow. It's quite costly. So if we're doing robotics, if we're doing on-robot learning, we have to actually wait for the robot to move around in the real world for potentially a very long time before we get any feedback. And in, for example, the science problems that I'm now looking at, a lot of the simulators are also quite slow. So it can take maybe a few hours to get a good estimate of the energy for a given atomic system. So that means if you have to do that for, I don't know how many samples there are in this plot, I don't know, that's not great. It's going to take a very long time. Additionally, there's also a real world cost to a lot of low reward states. So if you're doing robotics and your robot falls over, you have to stop your experiment, you have to walk over there, pick it up, recalibrate it, etc. That takes time. But in, for example, something like autonomous driving, you can really not learn from experience not to drive over people. There are certain states that you always want to avoid. So in general, we care a lot about data efficiency. And the perspective that I take on this problem, and a lot of other people also take on this problem, is that not all data is unique. And not all reinforcement learning problem states are also going to be unique. So some examples that I show here, you have Carpool. If you're familiar with it, it's like a little cart that drives left and right, and you have to balance a pole. In the situation on the left, we're moving right and the pole is falling to the right. It's kind of a similar but flipped version of, moving left and the pole is falling to the left. And similarly, if we have some grid world and we're on a specific location in this grid world, then it doesn't really matter what color the floor is, right? The decision-making problem is still the same. And I'm at Microsoft Amsterdam, but I work with a lot of people in Cambridge. So if I develop my autonomous vehicle in Amsterdam and I want it to drive me to Cambridge, I want it to just be able to generalize to driving on the wrong side of the road and not, have to learn all that from scratch again. So I'll give you a little bit of background just to make sure we're on the same page when I'm going to talk about the meat of the talk. So first off is, what is a group? So formally speaking, a group is a set with a binary operation that obeys the group axioms. And this set will very often be in the type of things that we're talking about today, something like a group transformation. So we have a set of translations, we have a set of reflections, we have a set of rotations, for example. And the group axioms state that, well, for one, you have to have some identity element. So if you're looking at rotations, you should have a 0-degree rotation in your group. You should have invertibility, which means that for every element in the group, its inverse should also be there. So if you can rotate to the right, you should also be able to rotate to the left. Closure means that if we apply this binary operation to two elements in the group, then the result should also be an element of the group. And associativity means that, it just doesn't matter where we put the brackets. So I want to give you a bit of context for what I mean about symmetries in reinforcement learning. So this means that for all states and actions and for all group elements, the dynamics are invariant under the group transformation. So what does it mean? It means that if we compute the reward of a given state action pair, it should be exactly the same as computing the reward for a transformed state and a transformed action pair, right? If we rotate it, it should give us the same reward. And similarly, the probability of going to S prime from S and A should be exactly the same as going from the probability of going to a transformed S prime from a transformed S and a transformed A. So I'm showing here a little grid world example from older Ravindran paper. So are there any state action pairs here that you can identify as being symmetric? Yeah, exactly. There's a symmetry over the diagonal here. So for example, state A and state B are symmetric if we also take into account the actions. So if we're in state A and we go up, it's kind of the same thing as being in state B and going right. Note also, before I forget, that this is a recursive definition, right? It would not be symmetric if the states that follow are not symmetric. So given that we have a symmetry along the diagonal, it means that we can, in principle, find a smaller MDP where we've kind of folded over this symmetry, and we can do our planning there, which should be more efficient because it's a smaller space. And importantly, if I have symmetric state action pairs SA and GSGA, that means they have the same optimal policy. And that's kind of important because that's what lets us do all the other stuff. So equivariance is also a big part of what we're talking about today. So some context there. In equivariance, this was first developed for like supervised learning type stuff. If you want to build an equivariant network, you want to be able to say that, you know, if I take my input, which may be an image of a dog, and then I rotate it, and then I map to feature space with my network, I want to end up at the same point as if I map to feature space first and then do an equivalent transformation in feature space. So this square is what we call a commutative diagram. And this f of gx equals g prime of fx, that's like an equivariance constraint. Okay, so far so good? Everyone's still on board? Awesome. Okay, so I want to first talk about this paper, MDP Homomorphic Networks, which I did with Daniel, Herke, Frans, and Max. This is about exactly this, like group symmetries in reinforcement learning. If we know there's some symmetry in our reinforcement learning problem, how can we then use this in policy learning? So I want to introduce to you what an MDP homomorphism is. So let's start with what a regular homomorphism is. So in general, homomorphism is a structure preserving map between similar algebraic structures, such that if we apply an operation to X and Y and then map to a different space, we end up at the same point as if we would map to the different space first and then apply the operation there. So this already sounds very familiar to what I was telling you before, right? So some examples are a linear map between vector spaces, an exponential function between the reals and the positive reals, and also a group representation. So then it's from there not such a huge leap to an MDP homomorphism where the algebraic structure is just two MDPs and the structure preserving is preserving the dynamics of the MDP. So we have some ground or original MDP. In this case, it's the Carpool problem again, where we have some symmetry over the vertical axis. So we say, okay, SA and GSGA are again symmetric state action pairs. And now an MDP homomorphism is a map from this MDP to an abstract or reduced MDP where we've kind of folded over the symmetries. And again, that's attractive because these symmetric state action pairs have the same optimal policy. So what we did in this work is we identified a few problems where such group symmetries show up in reinforcement learning. And then we're trying to see if we can get improved data efficiency by exploiting these symmetries. So the observation we made is like, look, if you have your Carpool problem and you flip it over the vertical axis, and then you compute the policy for the left and the right action, you kind of want to end up at the same point as if you would compute first the policy of the original state and then just flip the actions, right? That's a pretty intuitive concept. So you can write this down as a generic equivariance constraint saying, you know, if I apply some permutation to my policy, I want to end up at the same place as if I would compute the policy of my transformed state. So these MDP homomorphic networks exploit these symmetries in reinforcement learning problems. So what we do is we bridge MDP homomorphisms and equivariant networks. So particularly, we look at group structured MDP homomorphisms, but an MDP homomorphism is actually a much broader class of maps. So we create deep networks that are constrained by these group structured MDP homomorphisms and enforce the types of equivariance that we care about in this problem. And we also, because it can be kind of annoying to sit down and derive the the equivariant network, unless you're like really into that stuff. We also introduce a method that's called the symmetrizer that will take your weights and map them to an equivariant subspace. And this will allow you to more easily construct an equivariant network. So we evaluate this on a bunch of problems where we see that there are some symmetries. So one is Carpool, one is grid world navigation, and one is the Atari game Pong, where you have a symmetry over the horizontal axis. And in these evaluations, higher is better because it's the average cumulative reward on the y-axis, and on the x-axis you have the number of time steps. The green curve here is the equivariant or MDP homomorphic policy network. The red is sort of a standard type of network, like your normal MLP or your normal convolutional network. And the gray one in Pong, that's a data augmentation baseline. So you can see that you need fewer interactions with the world to get to similar policies if you exploit symmetries that are inherently in the problem. And data augmentation, importantly, also helps, but just not as much as building the equivariance into the network. And this is something that other people have also observed later on. So we need fewer interactions to obtain good policies with MDP homomorphic networks. This is useful for RL problems that exhibit group symmetry. Now, a question I very often get is, what if my problem is actually asymmetric? Well, then I think you should probably not use this, because what you end up doing is you exclude the asymmetric policies from your set of from your search space of policies. You've excluded the asymmetric policies, which means that if your optimal policy is asymmetric, you're not able to find it anymore. And I've not gone into much detail about the symmetrizer, but if you're interested, you can use this to construct your network for you, and the code's online. Any questions so far? Yeah.
So in one of your previous slides, you were showing some examples of Carpool and then also the 4-element symmetry group one, that's the grid world.
Yeah.
So I was wondering with your experiments, when you're observing like the sample efficiency on different data sets, is it usually the case when it's like the more elements you can find symmetries in, the more efficient, the more data efficient using equivariant methods? Yes.
I think that's the case. I haven't done extensive experiments, but the more elements your group has, the more you've constrained your search space, like the more you're folding over, basically. So the easier it is to find a good policy.
Problem, apart from considering consider state verifies this one, just multiply the quality by a scalar and have a stronger preference to go that way.
Right. I mean, I think that could be a sensible inductive bias. I haven't tried it. It's something that we've thought about, but never really got into, this concept of being equivariant in some way to things that aren't so nicely group structured. You could imagine that if you learn how to drive along a road, let's say right now it's cold and snowy outside, you maybe always want to reduce your speed, right? It's like a scalar multiplication as well. The problem is that it's maybe not so easy to put these constraints in a neural network because the group has a very nice structure that makes this super easy.
So my question is, all of these symmetries you like specifically said are symmetries, right? Like you're hard coding these into the set. Is there any way to like learn them maybe?
Yeah, some people are looking at that, definitely. I would say it's quite a hard problem, especially for reinforcement learning. So it's a graph isomorphism problem. So that's the type of problem, the type of solver you could use to do this if you have a discrete MDP where you know your transitions and you know your rewards. But for a lot of real world problems, you will not be in that situation, and then it's a lot harder. I think in supervised learning, people are doing some of this stuff. I happen to know that a few guys that are working on this, and they're not getting super far. So I think it's a very hard problem, but you're starting to see the first sort of literature come out about this.
Like intuition as to why, so data augmentation doesn't work as well as including the symmetry? Is it just a matter of efficiency, like needing less training samples, or?
Yeah, I think because you still have to learn the symmetries, right? You're just giving it some extra rotations that it can more easily learn from, but in the end, it's not baked into the network. So you're kind of shortcutting a lot by baking it into the network. I will say that it does depend on your problem what the right approach is to use. I think there are, I want to say in PDE modeling, people have said that maybe data augmentation is better, but in settings like this, reinforcement learning, where you want to be very data efficient, I think most of the related work has found that equivariance is better.
Thank you.
So my question is about the symmetrizer. I didn't quite understand that. Like, for example, in the Carpool example, we can kind of take the negative of the position and negative of the velocity,
Exactly,
like a function, but how does that affect the network? Like, what does the symmetrizer do? Maybe I just didn't understand.
Yeah, it's a bit my fault for talking about it, but not actually talking about it. Basically, what the symmetrizer does, it takes as inputs the transformation of your inputs, and it takes as input the transformation of your outputs of your network, of a given weight matrix, let's say. And then it sums over all the group elements. And this is kind of a projection onto an equivariant subspace. In a different talk, I had a whole slide with some intuition, but I thought, no, I'll just do the RL part today. So I'm very sorry about that. But basically what you do is you project onto the equivariant subspace. But then of course, you're not constrained to stay on this equivariant subspace during training. So what we also do is we just compute a basis for the equivariant subspace that gives us some basis filters, like basis weights. Then your actual weight becomes a linear combination of trainable coefficient and fixed basis weights. And this ensures that your network weights are equivariant.
Thank you.
Which is, could pre-training the network over the symmetric parts of its states produce a faster training speed, even if the target is asymmetric?
I think so. So that's also something we experimented with, where you say, I'm just going to use equivariant representations and learn just a regular old policy on top of that. And I think that can also help, because at least you've sort of not learned the symmetries in the, for example, let's say your transitions are symmetric, but your reward function is not. That could be a setting where you would want to do that. All right, let me check quickly how I'm doing on time. Okay. All right, so after the single agent MDP homomorphic networks, we got quite interested in seeing if this could also be useful for a multi-agent setting. So this was work that we published in ICARL 2022. This was with Herke, Frans, and Max. You'll see that Daniel's no longer here because he went to industry while we were still at the university. So we had to do without him. And here we were very motivated by the concept of cooperative multi-agent systems. So let's say you have a drone swarm that's wanting to do some search and rescue mission or something, then you could treat that as one big swarm, but you could also treat that as a bunch of individual agents that have to cooperate with each other. And traffic light control, as I mentioned before, you could treat every agent, every traffic light as its own individual agent. And then they also have to work together because most traffic networks are way too large to do some kind of centralized control. So the setting that we're in here is that of centralized training and distributed execution. That's a quite common setting in multi-agent literature. So let me give you some context. So a centralized controller, what we mean with that is that you have some kind of puppeteer agent. And this takes all the observations from all the individual agents, then reasons about them in some way, and then returns to every agent like a policy, a local policy for the agent to use. So everything has to be sent up and then everything has to be sent down. But of course, there are many situations where you don't want to do that. So we contrast it with the setting of distributed control, where you have every agent takes its own local observation and maybe some messages it receives from nearby agent and takes decisions locally, only from local observations and local communications. This is what we call the distributed setting. sometimes in the literature you will see like the decentralized setting. So it depends a bit on what definition you use. We use the definition that in a distributed setting, it's local control with communication. Decentralized is local control without communication.
Do the different controllers know where they are with respect to other controllers?
Do the different, in what sense?
So like does track like 1 know that track like 2 is on the same road, let's say?
It's part of the geometry of the problem. So once you start putting that kind of geometry in, they will know. You do need some kind of spatiality for this to work. Yeah. So we're interested in global symmetries in multi-agent decision problems. So symmetries that are not just local to a specific agent, but that are a feature of the whole global system. So if we take the traffic light control problem, we could say, okay, what if the distribution of cars over the traffic network is rotated? So the agents stay where they are, but the features, the cars that you see, they are rotated. That's a global symmetry of the problem. And here we kind of say, okay, if there is a global symmetry of the state space, then there should also be some kind of global permutation of the action space of the joint policy, right? So the policy that agent 1 is doing on the left should probably not only internally permute, but also move to a different agent. So that's a global permutation. And we can write down an equivariance constraints on global states and joint policies in a similar way as we did for the single agent case. So we know that this has been successful for the single agent case. So we might naively say, okay, we just put like, for every agent, we use a sort of equivariant convolutional network to compute the policy, and then we're happy. But that's not exactly the right answer, because if you do a bunch of local rotations and then you stick them together, that's not the same thing as doing one global rotation. It doesn't give you the same solution. So we can't just do this super basic local equivariance. And otherwise, the single agent approach would only be applicable if you use a centralized controller that takes all the input at the same time and is able to therefore globally enforce equivariance. So the observation we made here in multi-agent MDP homomorphic networks is that you can actually use global symmetries with only local computation and local communication if you set your equivariance constraints right. So there is a way to have only local equivariance constraints that does allow for this global distributed symmetry. For this, we use the fact that you can use message passing networks to do distributed execution. So if you're not familiar with message passing networks, they're kind of a generalization of a graph network. If you're familiar with a message passing algorithm like belief propagation, for example, this is kind of a neural version of that. So message passing networks are very suited for the centralized training distributed execution setting, because you just train them as a standard network at training time, but at execution time, you can distribute all the parts of the network onto different devices. So one part of the network is that you have a local encoder that takes a local observation of an agent and encodes it into a local state representation. Then when you start doing the message passing, you compute the messages just based on your local state representation and maybe the edge information between you and your neighbors. But there's no centralized thing going on here. You aggregate the messages. You can do that on your own device. And then you update your local node, for which you also only need your local information and the messages you've received. And then finally, you will compute the policy locally based on your current node status. You train this in a centralized way, but at execution time, you can just copy all this onto different devices. So the question is now, how do we use this to get like a globally equivariant network that's able to do distributed execution? So it turns out you can do it as follows. You place an equivariance constraint on your encoder. This makes sure that the symmetry information in your observation, your local observation, gets stored. You also put an equivariance constraint on your messages, which means that the symmetry information that your neighbors have is passed on to you. Then, of course, you do an equivariance constraint on your node updates to make sure that the information, the symmetry information you have locally and that you've received is also passed on to your next state representation. And finally, you have an equivariance constraint on local policies, which makes sure that, in the end, your policy is actually equivariant. So these local equivariance constraints actually allow you to do a distributed global symmetry.
Okay. Now you're about to discuss the application. I can ask about the chat like
yes. Do you want to see?
You have, like, let's say 4 nodes that you train the global rotational symmetry. But you want to ensure that every local node encoder, which let's say is CNN, is like a rotation equivariant CNN. And then this setting means that after you train this with all these equivariances placed locally, you can then make every chat like do its own local encoding and classical status and with respect to global equivariance.
Yes. So I think actually this is very related to what, if you're familiar, what they do in like a tensor field network, for example, where you have a rotation of a vector field. So this is very similar. I never actually wrote this in the paper, but I think it's a very similar setting. Okay, so we did some experiments. The wildlife monitoring experiments, kind of variant of a predator-prey problem. And we also have a traffic light control setting, just because it's cool, but also because it's like a difficult coordination problem. So if you're all sending the cars onto the same road, you're going to get congestion, which makes it very hard to get out of and also very hard to learn from. Oh, sorry. So for evaluation, okay, we look at these 2 problems. In the wildlife monitoring setting, higher is better. That's just the average return on the y-axis. And again, the green is sort of the equivariant or MDP homomorphic network. In this case, the red networks are actually a message passing network that's data augmented. And the gray network is just a standard message passing network. So we did give the baselines the graph structure of the problem, right? We're not giving it just a completely stupid MLP or something. For traffic light control, lower is better because we're plotting here the average wait time of vehicles in the traffic system. And that's what we would like to reduce. And you can see in both cases that, enforcing the symmetries that are present in the problem actually helps us with data efficiency again. And importantly, also, symmetry by equivariance improves over symmetry by data augmentation. Especially in traffic light control, there's quite a big difference. And I think that's because the coordination problem is quite difficult. So if you run into like a good policy one time, you want to make sure that, you can immediately replicate this for all rotations of your problem. So to wrap up this part of the talk, we enforce this global symmetry equivariance with only local communication and local computation. And this helps us with data efficiency, especially if we use it as an equivariant network. So to end the part on the MDP homomorphisms, both in the single and multi-agent case, we need fewer interactions with the world to get good policies. And you don't just have to take my word for it, because other people have been doing very similar things and finding very similar results as well. So one is this work from Northeastern, I think it's on sample efficient grasp learning, where I think they actually do on robot learning pretty fast using equivariant models. Another is molecular design. There's a lot of 3D rotational symmetry in a setting like that. There's also been some extensions, for example, to continuous MDP homomorphisms, and also working on like learning equivariant representations to make RL more data efficient. Okay, any questions so far? No, this is all super clear, right? Like, okay, awesome. So I also want to just briefly highlight this work that I honestly only had a very small part in, but I think it's kind of a neat result that we get here. So just wanted to weave it into this talk. So this was led by Darius, but also work with Christian and Shimon and Jacob. I think they're all at Oxford, or yeah, Darius may not be anymore. We presented this at NeurIPS actually 2 weeks ago. So to illustrate the problem, I will talk about this lever game that was introduced, I think, by this other play paper. So if you and a random unseen partner without communicating, choose the same lever, you get the payoff that's indicated on the button here. Otherwise, you get a payoff of 0. So which lever should you choose? Huh? Yes, well, thank you for spoiling it. Yeah, so there's a problem here of mutually incompatible symmetry breaking. If we want to get the +1 payoff, but because we don't know what the other guy is going to do, we don't know which one we should choose to get the optimal payoff. So then the rational thing to do is to go for the one lever that's different. So this is a problem of zero-shot coordination. So the goal of zero-shot coordination is to train agents that are able to coordinate out of the box with new partners without necessarily having a shared language, and also without joint training. So you cannot assume that you're able to train together and fine-tune to each other and get super specific joint policies. It has to be somewhat robust to getting a new partner. Now you can ask like why this seems like a more theoretical exercise, but it can come up also in the real world. For example, if you have to coordinate with other agents that have very different, I don't know, systems, they're from a competing manufacturer, for example, or if you need to coordinate with human beings who don't want to sit down and train together with you, you just have to, you just have to work. And it's very common for like a lot of the multi-agent work that you might have seen to be more in a self-place setting where you're playing with, even a cooperative setting, or against in a competitive setting, older copies of yourself, or maybe even current copies of yourself. So you get better and better at defeating yourself, but you also might end up overfitting to yourself. So crossplay, on the other hand, is about playing with or against an arbitrary collaborator with a potentially very different policy than you, and you cannot assume that you can perfectly tune to each other. So a solution to, for example, the lever game is to treat all the symmetric levers as a single equivalence class, right? The expected payoff if you do that is maybe 0.1, whereas the other lever has an expected payoff of 0.9, and then it becomes a very simple problem again. Okay. So if we have two policies and they are what we call symmetry equivalent, which means, for example, that it's just a permuted version of the other policy. So if I have a deterministic policy, I assign plus like a probability of 1 to the blue lever, and the other guy assigns a probability of 1 to the orange lever, then if I permute the actions, it's again the same policy. That's what symmetry equivalent means. Then if we would if we assume that pi1 is equivariant to the same permutation, we can actually show that they have to be the same policy, pi1 and pi2. So this means that we've aggregated the symmetry equivalent policies, and instead of having to think about crossplay, this now reduces to self-play within this symmetry equivalence class. I assume that this is still a little bit fake, but I promise you that the proof is in the paper. I didn't just make this up. And the way we end up using this is by doing something that's called the Equivariant Coordinator. And this is actually a variant of the symmetrizer that I alluded to before, where the symmetrizer takes a weight matrix and projects it onto an equivariant weight matrix. This instead takes like entire networks and projects them onto equivariant versions. This has some nice properties that are related to the symmetrizer. I'm not going to go into those, but importantly, like proposition 3, you can see the pi1 equals pi2 thing. So we have the proof for that in the paper as well. So we test this on zero-shot coordination in Hanabi. If you're familiar with it, I have never played it myself, but it's a apparently quite complicated card game. And it turns out you can improve existing agents to be better at zero-shot coordination by using the Equivariant Coordinator. So here's some results. So XP stats refers to crossplay stats, so higher is better. Bombao rate stats refers to, failing at Hanabi. So you're bombing out, so lower is better. So we take some agents that are trained for self-play, like these algorithms, and we take some agents that were trained for cross-play, like OP is other play, which is the paper that I talked about before. And then we compare, how do they do at crossplay out of the box, and how do they do if we symmetrize them with certain subgroups of the permutations of the cards. The takeaway here is that you can improve this zero-shot coordination using the Equivariant Coordinator, either for agents that are trained to be good at self-play, but also agents that are trained to be good at cross-play, and even agents that are trained with a data augmentation of the type of symmetry that's inherent in this problem. Okay, so takeaways. The problem that we're looking at here is mutually incompatible symmetry breaking for zero-shot coordination. If we use equivariant networks the right way, this exactly solves the symmetry breaking problem. We can wrap the symmetrizer that I talked about before to wrap entire networks into the equivariant version. And you can use this equivariant coordinator to get improvement in zero-shot coordination on, at least on Hanabi, but hopefully also other things. To go a little bit back to an earlier slide. So this geometry that I talked about today, you can really find it everywhere in decision-making problems. So I talked about the single and multi-agent setting before. Here are some follow-up works as well. There's even some works on, for example, embedding it in planning algorithms and stuff like this. And now it also turns out that you can use this to improve zero-shot coordination just out of the box. I think that's very cool. I think it's a super exciting field, and I'm really looking forward to seeing what people are gonna come up with next. But another thing I wanted to talk about is AI4Science. So if you have any questions about the previous part, this will be a good time to ask them.
Maybe it's a bit those questions, but when you train with using crossplay, the agents you train with, how are their policies determined? Are they random or are they trained?
So I think, for example, in other play, what they do is they train against randomly permuted versions of their own policy. So that's already taking the symmetry equivalence into account. What the other algorithms do, I'm not 100% sure because it's not really a field I usually work in, but I think those details are also in the paper. Yeah. All right. Yeah, so AI4Science, I recently started working on it, and it's I didn't know much about it like 6 to 8 months ago, but it turns out it's a really cool field. So I just wanted to share a little bit about that today. And I want to motivate that a little bit by talking about catalysis. Are there any chemists in the room? Awesome. Okay, so no one will know that I'm not a chemist either. A catalyst is a substance that increases the rate of a chemical reaction, but you can still, recover it afterwards. And catalysts are very important for all kinds of things, especially in industry, and they're very, very important part of the European economy as well. That's a sort of economic argument to care about catalysis, but I think it's also quite nice because it can help us, clean water, clean the air, come up with clean energy and better fuel sources, grow food more sustainably, etc. So besides the economic argument, I think there's also like a human component that makes this very important. So if we can find better catalysts and more efficient catalysts, and I don't know, all kinds of problems that we could solve. And problems like finding new catalysts, but also a lot of other things like drug design, for example, are very often tackled by the field of computational chemistry. And it's a branch of theoretical chemistry that uses computer simulations to solve chemistry problems. So some applications of this are, for example, to design new catalysts, new materials, new drugs, but also to predict the properties and outcomes of chemical reactions. So let's say you do come up with a new molecule or a new drug to predict how it's actually going to behave. The problem, however, is that most of the accurate methods are only feasible for very small systems because they just take so long to run. There ends up being a significant trade-off between computational costs and also accuracy. And now people in AI4 Science are saying, okay, well, we know that machine learning has done some really awesome stuff for language models, for computer vision, etc. Can we take some of that amazing power and bring it to these scientific problems and make some real impact there? So it's basically saying, okay, these machine learning approaches might be able to get us to an interesting new point on the Pareto front between computational cost and accuracy. So some problems that people are doing in this type of field is, for example, you would take your a system of atoms, so that's a 3D point cloud, and you would predict the energy of the configuration of atoms. Another thing that you might be able to do is take some molecule, maybe a drug that you've designed, and try to predict, is it low toxicity or is it going to kill people if I give it to them? And finally, another thing that you could do is if you have a partially constructed molecule, you could try to predict, what type of atoms should I place where in order to get molecules with a desired property. And that's kind of the task of de novo design. And you can do this with reinforcement learning or planning. But I talked to a lot of guys today about quality and diversity, so that might also be an approach that you could take. I don't know, I haven't tried. And the goal here is to construct molecules that have some desirable properties via some scoring function. So your state here is your partially constructed molecule, and your action is, placing a new atom on the molecule. Until at some point the agent should say, okay, stop, I think it's done. And then we evaluate it with some domain-specific score. Okay, domain-specific score is a bit of a load-bearing term because actually defining how good a molecule is very difficult. For drugs, for example, you have to do actual tests on people to know if it's actually going to fix their problem, right? So you don't really have access to the ground truth. But the nice thing is that if we're designing in 3D, it's very highly rotation symmetric, so we can make a little bit of use of that. Applications for this are everywhere, like drug design, but also coming up with better batteries or better catalysts. If you're into this, there's some work already in this space where they use like reinforcement learning or planning algorithm to design molecules. Of course, it's very nice if you're able to design a molecule in silico. Maybe you're even quite sure that it's going to have some desirable properties, but there's absolutely no use to this if there's no route to synthesize this molecule. If there's no set of compounds that you can iteratively react with each other to actually get to this target. So that's where retrosynthesis planning comes in. So the goal is, okay, we have some target molecule. Now we're going to iteratively search, okay, I know I can get this target through this reaction that has these ingredients. Now I'm going to see, can I buy these ingredients or do I already have them? No, then I'm going to search a step further until I find a route. So the goal is to iteratively find these buyable or available building blocks that in the end will react to the product that you desire. So reward is somewhat difficult to specify also here. You could, of course, just assign a reward if you find a successful route, but maybe also want to minimize the financial cost of all the compounds that you would have to buy. Maybe there are certain reactions that you're a bit uncertain about or that you think are a bit dangerous, so you want to avoid them. You would probably prefer a balanced route rather than one that requires you to do 100 different reactions. And you might want to avoid or prioritize certain types of chemistry. So in retrosynthesis planning, the transition function is assumed known. It's assumed that you know that these compounds will react to form this product. But are they? It's obviously a rhetorical question. No. Very like our chemistry knowledge is not that perfect that we will always know this, right? So yeah, before I move on, there's already some work in this space as well. So this is where reaction modeling comes in. So if we have a system of a bunch of different atoms, so this is again a point cloud of atoms in 3D, we might want to find all the bond changing stable configurations of this system. Bond changing means that either a bond is formed or a bond is broken from our starting point. Once we have that, let's say we have a stable start and a stable end configuration, we might want to predict the reaction rate, like how often do you actually get this reaction in practice? And this can help us, for example, in retrosynthesis planning. So this requires us to look at the potential energy surface. So this has as input our system of atoms. And as output, it would predict the energy of that given configuration. And then the local minima of the potential energy surface are the stable configurations of the system. And it's also highly symmetric, right? If we rotate the molecule, it will still have the same energy. So this is what we do in exploring reaction networks. So we're trying to find all the relevant minima of a potential energy surface. So reward could be something like, okay, if we find an interesting new minimum, we get a positive reward, otherwise we get 0. But this is extremely sparse and it's also non-stationary. So applications here are reaction modeling, for example, in catalysis, but also to help improve retrosynthesis planning. Also highly symmetric. So there's also in this space some work on using reinforcement learning to search through this potential energy surface. So, yeah.
So if I understand correctly, it seems that there's multiple different ways you could decompose the problem of like finding a synthesis pathway for a new molecule. So firstly, you may just like take the monolithic approach of having one network, like an RL agent that starts from nothing, and add it incrementally. That takes you to a molecule that is synthesizable and useful for some target. Or you can break it down all the way to having a network that's literally responsible for, given this molecule, what are the possible edges I could add? This is how much it would cost me in terms of the like potential energy and that's like the reaction rates. And you have other networks doing all the different bits to give you the full pipeline.
Mm-hmm.
And so which of those two kinds of approaches are you actually more excited about?
I will be very honest and say I don't know yet. I'm reasonably new to this field, so I'm not 100% sure what's going to end up being the best thing. In general, I like modular approaches, but I don't know if that's the right way to do this.
Okay. Another was like Carpool. I think they were saying that the more that you can put into the neural network, the better, rather than having lots of different like explicit bits. But of course, that's like fundamental physics things that you really don't want to do with the network.
Yeah, I wonder also if that wouldn't take like a lot of data to train. And data is very expensive in this setting. Or at least good data is very expensive. Okay. So this is pretty cool. There's a lot of stuff that we can do, but it's also very challenging. So I've dubbed this now RL for science, but maybe it should be more like decision making for science. So this is a basic sort of starter one. It's like we're in continuous and high dimensional state action spaces. That's not unlike what you see in robotics, for example, except that it's maybe a bit more high dimensional. But I'm not sure. Maybe the roboticists disagree. Yeah. Awesome. Okay. Usually we also want to be able to generalize between systems. So if we're just going to search like one very specific system, then we just might put, I don't know, turn on a regular search algorithm and just run it for a year and be done with it, right? We don't have to develop a whole machine learning method for it. It's often quite difficult to specify the MDP. We don't have a ground truth reward function. We might also not have a ground truth transition function. And also, we usually don't have access to the real world. So we very often don't have access to a wet lab that can cheaply check things for us, right? For example, if we would design a molecule by iteratively placing atoms, we don't necessarily even have a way to synthesize this molecule, let alone test if it's good. So basically, we're stuck right now to doing everything in simulation, but simulators are often either inaccurate or they're expensive. And for certain systems, they're both at the same time. And in general, data efficiency for that reason is going to be really, really important. However, that just means that there's very, very many interesting fundamental challenges that are left to be solved. And what I think is also quite exciting is that there's a potential for real and meaningful impact here. Takeaways, I'm almost done. So we'll talk about symmetry in decision making. This improves data efficiency for decision making problems. And there's many such problems in science. And symmetry and structure are also everywhere in science. So this seems to me like a match made in heaven. AI4 Science, I think, a fundamental research field with a potential for some meaningful impact, which makes it very exciting for me to be working in. If you want to ask some more, I don't know, specific questions about this or about the other symmetry stuff, again, you can find me basically anywhere. If you're interested in AI4 Science, hit me up. But if you're interested in science for AI, then I want to tell you a little bit about the ICLR workshop that we're organizing. It's basically on physics for machine learning. So if you get some inspiration from physics to improve machine learning, Equivariant networks will be one example of this. Then it might be a good fit for this workshop. Thank you so much for listening.
So thank you for the great talk. Do we have any questions? We have a question online. Contrary to what we were saying earlier, Lucia suggested that for what you were just saying, population-based algorithms might work better than RL due to sample efficiency.
Someone told me today that the population-based methods are worse at data efficiency.
I don't know.
Can we get an expert opinion on population-based methods?
Yeah, it's a very biased opinion on population-based methods.
Sure. It depends on what is meant by population. I mean, we kind of return the question, but it depends on what you mean by population-based methods. I mean, in most of our case, to optimize the systems, we need to estimate the gradients, and there's different ways to estimate it. And one of the ways is actually to sample around it and then use this to estimate the gradients. But to do this, actually, we need to do way more evaluations. So it's not very sample efficient in this sense.
Right. I also have another question. You said that there isn't much data available, but do you mean that existing sort of physical simulations for molecular energies, let's say, is the problem that they're just very hard to do, or that they don't give you very accurate energy surfaces?
Depending on the system, it could be both. So if you want to use density functional theory and you have a reasonably sized system, that can already take a few hours for a single energy evaluation. And then DFT is not even always accurate. It's not a ground truth calculation. So that makes, yeah. I mean, you could have very cheap, a lot of simulation. But one thing that we also talked about today is, for example, if you do robotics in simulation, you could get stuck in policies that exploit the quirks of the simulator. And I can imagine that something like this could happen in science too.
Yep.
I just had a question about sort of quantifying the symmetry in MDPs. So for example, if you have like a discrete state MDP, then it's quite simple. You could sort of maybe look at like how many times you can fold over, and then look at the smallest MDP you can get. And you could sort of say, you could quantify the amount of symmetry in that way. But if you have like a continuous sort of MDP, you could fold over and like a large number of times and still have an infinitely sized MDP essentially. My question is if there's any like way to meaningfully quantify the symmetry, and if you've tried some experiments to see like if the data like efficiency scales roughly as you would expect to with the symmetry of the system.
So you mean for the continuous setting as opposed to discrete setting?
Yeah, for either. I mean, if you tried experiments for either. I'm just thinking maybe continuous might be like slightly more challenging to quantify perhaps.
Yeah, I have not worked on continuous symmetries much myself, especially not in the RL setting. But some people have definitely done this, right? They have some kind of spherical harmonics that they put into a network. But I don't know. Yes, I think some of the guys at Northeastern have actually looked at this. So I have like a continuous rotational symmetry in a robotic setting, for example. And I think there also they get a pretty good data efficiency improvement, also compared to data augmentation, for example.
Because like the reason I'm asking this question was because for some of the environments we were considering, like there was maybe like reflection symmetry, say, but like for others, like you can have a lot more symmetry. Sort of, you might end up with a lot, like an effective number state that is a lot smaller. So these methods might be even more sort of applicable. So I was just wondering whether you could quantify that, like how well you expect it to work.
So I will give my cop-out answer and say that I think it depends on the problem. So take the example of having a rotation equivariant CNN for, I don't know, classifying pictures of cats and dogs. I would not expect a super large speed up there or improvement there because, very often the image that you get will not be a cat upside down. It will just be the cat in the original orientation, right? So how much the symmetry actually helps you depends on how much the symmetry actually shows up in the problem. So in a molecular setting, for example, you could imagine that you could see the molecules in every whatever orientation, right? Because they're just bouncing around in space. But in robotics, for example, what you will see is that you have a gravity element. That means that certain rotations of your state you will just never encounter. So it's not going to help you that much to bake them in. Do I have like a theory of how to quantify that? No.
Okay, right. So I guess it would be like an interplay between sort of the number of symmetries and the density of where in state space the observations
Yeah,
are.
because I mean, having this equivalence in your state action space only helps if you actually encounter different things in this equivalence class. Otherwise, it's just like the original problem.
Sure. Okay.
Anyone else?
Hey, thanks very much for the talk. I might have missed this, but for the retrosynthesis pathways, are the actions like from some database of like smile strings, or is it like in an actual simulation you're adding in like an action is to add in this extra atom and make it react in some way? Or
I think what they usually do is they have some database of known reactions that they come from. Yeah.
Okay, thanks.
Okay. Right, if there are no further questions, thank you again, Elise.
Yeah, thank you for having me.
We'd also like to thank our sponsor DeepMind for flying out Elise and paying for the sushi and drinks that you'll be enjoying shortly. If you're hungry for more RL, we have a reading group that runs every week, not during Christmas, of course. You can email us to join. And we'll be resuming next year on the 18th of January with Alessandro Lazaric from Paris, where he heads a team at FAIR. And he'll be talking about unsupervised exploration in goal-based RL. So have a good Christmas, everyone, and thank you.
Oh, can I say one more thing? If I really hyped you up for the AI4 Science, we just opened a new batch of internship positions. So definitely do apply.
Yep. Thanks.